something else.
Okay, cool. All right. Good morning, everyone. My name is Einat Lev, and like Albert said, I'm from Lamont Doherty Earth Observatory, which is part of Columbia University. And I want to introduce sort of a younger sibling, maybe, to CSDMS, and maybe trigger some, hopefully, collaborations. So Victor stands for Volcanology Infrastructure for Computational Tools and Resources. And by kind of definition or mission statement, it's a cloud-based platform for volcanologists to use, find, and integrate numerical models and other computational tools. The motivation for it, there's always been kind of a need for a facility like that, but the real kind of guidelines came from a 2018 National Academy report called Erupt, which really laid out the plan that the community requires an access to high-performance computing, state-of-the-art models. They needed to be communal, needs to be a community facility with accessibility and friendliness and efficiency, and a lot of really good wishes. So we don't come into a vacuum. In the kind of past decades, there was an effort called VHub, which tried to supply something of virtual cyber infrastructure for the community. It rose in popularity as training and support was going on, but then it declined. A lot of it because the infrastructure became expensive and hard to maintain and just didn't serve the community anymore. It was just kind of becoming obsolete, as many things in cyber infrastructure tend to do. So we said, okay, let's go back to the drawing board. What are the goals? The goals are to make it easier to run computational models and tools, broaden model literacy. We felt that a lot of people are intimidated by modeling because their first impression of it is that it's so hard to install Python libraries and they get stuck. But they don't get to actually understanding what it means to model. And then down the line, reduce volcanic hazards by making models more accessible. So we formed a team. We have a team at Columbia, which is myself and Sam Krasnov, our software engineer, and Sophia Sawinski, who is a coordinator for education and training, which, as we mentioned, is key for maintaining these things going. And co-PIs are Sylvain, Chuck, and Abani at Florida and Tufts. We also have an advisory committee trying to represent different parts of the volcanology community, from government agencies to international scientists at different career stages. These guys have served us for the last 3 years since we started and are stepping down now. And now we have a new committee that is just starting. Again, trying to represent, a postdoc, an international, and agencies and things like that. So what exactly is it? Similar to what CSDMS have, the core of Victor is a Jupyter Hub, which includes a big library of models, different workflows in forms of Jupyter notebooks, lots of tools for visualizations, compilers, and also examples of how to access external data sources like weather and topography and remote sensing and everything else that you need to look at a volcano. The website, victorproject.org, also includes information about events, workshops, demonstrations, collaborations, and Victor is being used for teaching in a lot of different universities and colleges. We also have links to our YouTube channel and with a lot of teaching materials. The sign up, authentication is using CI logon, GitHub, Microsoft, and Google are supported right now. And our documentation, which uses Read the Docs, and our Slack channel. I don't need to tell you that CSDMS has somewhat similar spirited effort, but there's others in the geoscience community, such as Pangeo for oceanography, Scope for seismology, the Alaska Satellite Facility is now for star data, Enki for petrology, and now there's a new one you may have heard of, the GeoLab out of EarthScope. So there's a lot of action in that territory, which is great. The technicality of the hub, it's running Ubuntu. It features kind of everything you need. So there's libraries and compilers and packages. So it really saves the users the headache of having to install and maintain these environments. The experience is familiar, I'm sure, to many of you. The login, you get a login screen. Can choose a machine. We have support for different, kind of a range of CPUs and memories, as well as GPUs. And the users see the Launchpad, which has a link to a virtual desktop, a graphical user interface. Many tools require that, as well as a beloved terminal for those who like that. We have a huge collection of pre-install workflows for a range of different tools, and they all wrap around kind of modeling tools that come in different languages and different approaches. For example, this is one of the notebooks for running lava flow models called IMAX, which is actually written, I think, in C++. And then the notebook starts with installing everything, runs the model, gives you kind of a basic visualization. But then because we also have the graphical desktop, we can load the results in, for example, QGIS, and show the model results on the Google Earth map, and everything is simple, and the user hadn't had to download anything. Everything is through the browser. So they got the DEM for Hawaii in the notebook, and then they ran the model in the notebook and visualize it in the notebook, and everything is hopefully much simpler. This is a list that's kind of hard to maintain up to date, but there's a list of the processes we have models for right now, from lava flows to density currents, all the way down to geochemical and magmatic petrological tools that deal more with the kind of deeper parts of the system. And that gets updated all the time. This is probably already out of date. Like I said, our documentation is using Read the Docs. So again, it's flexible, it's open. And we're maintaining a lot of educational materials. Some of it is basic training. What is Python? What is Victor? What is Jupyter? Some of it we got from CSDMS. Some of it we got from Project Pythia. You may have heard of that effort. We also have a lot of teaching modules that use Victor resources. A very popular one is a tephra dispersal aimed with kind of application. Is the building going to collapse under which volcanic eruption conditions? Or a lava flow one, when would the lava cross the road kind of exercise? So they've been tested in at many different institutions and levels. We're planning an educator webinars. If any of you are teaching any sort of geoscience class, we have a couple scheduled for this summer, so you're welcome to join and see what we have to offer. That's the tephra lab. Again, we ask kind of guide the students through the process. For the past 4 years, we've also run a computational volcanology class every spring, where we have participants from all over the world, which makes scheduling very difficult for the time zones problem. But about half of participants watch the videos after the class because they're from very different time zones. But we cover a range of topics from basic math, differential equations, numerical methods, to application. Go to your volcano and model a lava flow on it. We've ran workshops at conferences and also held a developer summit where people who develop tools came together, installed them on Victor, adjusted both notebooks and worked with our engineers to make it happen. We have another one coming up this fall. So if you think there's a tool that would fit, or you have a friend who has a tool that might fit, just let us know. One of our funnest activities last summer was a kind of a hybrid workshop where we went to Idaho, the Snake River Plain, which is a very volcanically active and interesting region in the Northwest, and have kind of like one day visit the lava flow, second day model and remote sensing the lava flow. Again, kind of alternating. So it was kind of a unique way of doing things. It's not just a hackathon. It's not just a field trip. It was really cool. And we used, University of South Florida has a brand new field station right at the edge of the Snake River Plain, very close to the Craters of the Moon Volcanic Park. So, and they rent it. So if you want to contact them, if you want to use it. Now, okay, so what's the point? The point, in my opinion, is having everything in one place, speaking the same language. So really the motivation for this came from me trying to benchmark lava flow models as I came into the community. And it was such a pain to find all the codes, get them all in one place, get them all speaking the same language. It was such a pain. I was like, this cannot be how we do things. So Victor came to be. So now we can compare different flow models on the same conditions, set up the parameters, run them all, compare them all, in really just click of a few buttons. A new capability that we got NASA funding for is having access to remote sensing be more simplified and streamlined. A lot of modelers sometimes have kind of an intimidation by NASA jargon, all the acronyms, all the satellites. We don't want that to happen. So like if you're interested in a lava flow, say in Iceland, you can square around, define the region of interest. It'll tell you what's available, mostly from the kind of higher level processed products from Project Opera out of JPL. And then we have some simple segmentation tools where you can look at the area of the disturbance over time. And now that we have models and data all in one place, the next thing to do is combine them and, for example, assess the quality and the fit of your model. So we use a new library called BAM, which gives you different assessments of the quality of your fit of the forward model and the remote sense data. Again, this is the Mauna Loa 2022 eruption in Hawaii. Another remote sensing capability that we kind of ingested is looking at using a tool that looks at tropomy data for SO2 emissions and can give you kind of like a time series and really simplify things. This was a tool that was initially developed for Google Earth engine. So we didn't do anything. We just took it, put it in. We can call the Google Earth engine API. Everything's the same. So it's really just kind of tying up the knots on everything. We're working on workflows for inversion. For example, this is for tephra data, where you can look at collection of tephra thickness layers in the field and invert for what the eruption conditions were, the plume height, the mass, and the grain size distribution. And you have a collection of different inversion algorithms to use, so you can start comparing things. And this is, again, it would have been such a pain probably to take a grad student several months to find all these codes, code them, get them to compare. And now it's streamlined. For more inversion examples, we have two different packages that look at deformation data, VMOD and D models, that you can provide them with GPS or INSAR or both, and they give you where's the magma chamber, what is it doing, and kind of simplified conditions and uncertainty on that. So one of the challenges I wanted to really talk to you guys about is right now, maybe you saw from the list, everything is kind of segmented. So what we have now for a volcanic system is we have lots of models for each of these pieces, and they're separated. And if we want to, for example, aim for having a digital twin of a volcanic system where we can monitor it and update it and assimilate data and all that, that's not going to cut it. So we're hoping to get into a system scale models where all these processes feed each other and interact. And this community probably say, oh, well, we've done this for a million years. So this is why we have a proposed collaboration between Victor and CSDMS, where we're hoping to adjust tools like the BMI and Babbler and all that, and bring it into the volcanic system. We're going to start small with kind of just a few one-directional coupling from the magma chamber up to the gas dispersal. We're missing a few pieces in this, but we're hoping to connect them later. And maybe also tie these into landscape models and geomorphological models where, if you have a big lava flow or PDC deposits, we'd put 20 meters or 100 meters thick layer on top of your river, what's going to happen? How long is it going to take to cut through? So that's kind of a down the line vision, but that's why I'm here and hoping to talk with all of you about this. So that's it. Thank you.
Thank you, Einat. That was awesome. Thank you. Are there any questions?
So can you speak a little bit more to how folks add new capabilities, or maybe like the funding structure? Like how how do you add new capabilities?
I'll repeat the question.
Yes. So there was two questions. One was how do people add new capabilities? And the second was about the funding structure. So for adding new capabilities, we have an interest form on our website where people who either develop a tool or want a tool that may be in the community just fill out the form, say what kind of basic information, and then our engineer contacts them, find out where it is. Is it on GitHub? Is it not? What testing has it gone through? What's required, and all that. And then we start kind of a process through that. So you cannot just upload just your own thing, because we need to build the image and we need to take responsibility for at least how it functions in general. We don't take responsibility for specific bugs in codes, because we didn't write them. For funding, so far we got funding from NSF. We started with an Earth scope kind of catalyst, small grant. Then we got an open science ecosystems grant to maintain for a couple more years. And we got, like I said, NASA funding to incorporate some of the remote sensing data. All of that is now coming to the last year of it, and we have proposals pending, and we're going to keep looking for money as everyone else is.
Nico.
Yeah.
Is that something that people pay for, or like what's?
Yeah, so far it's been free. Everything has been free. One of our ideas for sustaining this further is to start having paid services. We have talked with other kind of similar open science efforts like databases and things that from their experience, once you start asking people to pay, they're just not going to do it. Like if you ask people to pay to deposit their data on some database, they just won't. Sure, you can say, oh, but NSF would cut their funding, but they don't. So that's going to be a problem. And in the grand scheme of things, we prefer to keep it open and educate more people than whatever, $1,000 we'll get from registration. Yeah, but the people have the option of getting a certificate from University of South Florida for completing the course and the assignments. So that has been a motivation, for example, for folks who work in observatories and other government agencies around the world. So there's been some demand for that.